Hello everyone, welcome to In 5 Minutes. In this video we are going to see higher order differential equation with variable coefficients. So till now we saw the equation is always of the form x raised to n d raised to n into y dx raised to n plus x raised to n minus 1 d n minus 1 y dx raised to n minus 1 and so on till x dy by dx plus y equal to some x. So we know that this equation is nothing but Cauchy's equation. But now we will have equation something like this. Instead of x, we have px plus q the whole raised to n, and the derivative terms will remain the same, plus a n minus 1. Here we also have a raised to n, a n minus 1, a1, a0 and so on. Due to the presence of x as a coefficient of derivative, these equations are higher order differential equation with variable coefficients. Here also in front of derivative we have a term of x, but it is px plus q type. So this equation is Cauchy's equation. Then this type of equation where we have px plus q as a coefficient of derivative terms, then this equation is known as Legendre's linear equation. So in Cauchy's equation we substitute z equal to log of this term which is x. Similarly here we will substitute z equal to log of this term which is px plus q. In this case x is e raised to z, then in this case px plus q will be e raised to z. If I take q here, it will be px equal to e raised to z minus q. Then in this case x will be e raised to z minus q upon p. In Cauchy's equation we substitute x d by dx equal to d and x square d square by dx square as d into d minus 1 and so on, where d is d by dz. So here we substitute x d by dx equal to d. This x matches with the coefficient of the derivative. So here also we will substitute px plus q, the coefficient of derivative, into d by dx equal to d. Then in this case we also multiply d by coefficient of x. Coefficient of x in this case is p. Then px plus q, d square upon dx square will be p square into d minus 1. This term remain as it is. Here instead of x square d square by dx square we substitute px plus q d square by dx square. Here we substitute d into d minus 1. Here we substitute p square into d minus 1 and so on. Here also this d is d by dz. So this is the basic substitution for Legendre's equation. This will be more clear when we see the problem on this type. So the problem is this. So in this equation if you see we do not have x square term or x. Here we have 1 plus x something. So this equation matches with px plus q the whole square d square y by dx square plus px plus q dy by dx plus y equal to some function of x. So this equation is nothing but Legendre's equation. So for Legendre's equation we substitute z equal to log of this term which is 1 plus x. Then 1 plus x will be e raised to z and x will be e raised to z minus 1. Remember this. Then we substitute px plus q into d by dx equal to p into d. In our case, if we compare these two equations, we will get p equal to 1 and q is also equal to 1. So we are going to substitute this px plus q into d by dx will be p into d. So 1 plus x into d by dx will be 1 into d which is d. Then 1 plus x the whole square, d square upon dx square will be p square. P square is nothing but 1 square, d into d minus 1. So this will be nothing but d square minus d. So now we are going to substitute all these terms. So instead of 1 plus x square d square by dx square, we are going to substitute d square minus d into this y, plus instead of 1 plus x d by dx, we are going to substitute d which is d into y plus this y equal to log of 1 plus x, and we are substituting log of 1 plus x as z. So this will be nothing but z square plus cos of log of 1 plus x is nothing but z, so cos of z. So now from this equation I am taking y common. I will get d square minus d plus 1 into y equal to z square plus cos z. This d and this d will get cancelled and we get d square plus 1 into y equal to z square plus cos z. So as you can see, any higher order differential equation with variable coefficient can be reduced to this equation, which is f of d into y equal to z. This is the higher order differential equation with constant coefficients.